Okay, this is a short lecture about sulfide oxidation by these chemosynthetic bacteria, or what I prefer to call the chemolithotrophic bacteria, or chemolithoautotrophic bacteria to give their full name. This is both a review about these organisms and also provides a bit more information, an important piece of information about their physiology. And of course, we're spending so much time on these organisms because they are the prime producers at hydrothermal vents. They are the reason why we have such a luxurious and diverse community of invertebrates and other organisms at these vents. They're really unique ecosystems, and I think it's worthwhile understanding what's going on here. So you should know already that that all the life that we see at vents is supported by sulfide oxidation. And this sulfide oxidation, in this case, is done by bacteria, though archaea are also able to do it. And the sulfide itself, of course, comes from superheated seawater, in which the sulfate is reduced down to the level of sulfide. And that sulfide then creeps up back to the oceans through these cracks, the vents, and that's where we see these organisms. The sulfide is the electron donor, and the electron acceptor is oxygen. Now, I tried to get you to understand what was going on by drawing a parallel between what we do, that is, we are chemoautotrophs, we are carrying out aerobic respiration, in which the the electron source is organic material, not hydrogen sulfide, but the oxygen is still the electron acceptor. And so in chemolithotrophy, that organic material is replaced by some inorganic compound. And an important example here that we're talking about is hydrogen sulfide as that source of electrons. And so we need to revise this equation because it doesn't really completely give an idea about what's going on. And we revised it one way in which we showed that or discussed how this equation or this reaction yields energy that are used by the bacteria to support their own growth and in turn the growth of all the other organisms that are found at the vents. So one thing that's missing from this equation also is carbon. Where in the heck are the organisms getting their carbon? And now you know the answer to that. They are chemoautotrophs. They get their carbon from carbon dioxide. And so the full name of these organisms could be chemolithoautotrophs or chemoautolithotrophs. And depending on what part of the reaction that you are looking at, you can call these organisms chemoautotrophs, which emphasizes the fact that they are autotrophic organisms using CO2, or you could call them chemolithotrophs, emphasizing the fact that they are getting their energy from lithos, which is Greek for rocks, or inorganic compounds. And again, the compound of interest here is hydrogen sulfide. So as I mentioned, and as you should know now, in this literature, in this part of the marine biology field, people talk about these organisms as being chemotrophs, endosymbiotic chemotrophs, or which carry out chemosynthesis. And the reason why I don't like these things because those terms could be also applied to us. We are also chemotrophs. We get our energy from chemicals, just organic chemicals as opposed to inorganic chemicals. We also synthesize our biomass, our cellular constituents, by chemical methods, and we get our energy from the oxidation of chemicals, in our case, organic compounds rather than hydrogen sulfide, in the case of these bacteria that we're talking about. But the one part of that should be all familiar to you. But the one part of the equation we have not discussed about is how the carbon in CO2 is reduced to the oxidation state of carbon in the organic compounds. And so this is a shorthand. Again, of course, this is organic material, our favorite way of representing organic material. And in this diagram that we showed here, we talked about before, showing the parallels between photosynthesis and chemosynthesis, it just has ATP. And that's certainly necessary to reduce CO2 to the level that we see in organic material, but there's more to the story. So I've just blown that up now to kind of focus on this problem. The problem, though, is where the energy for this, the ATPs, come from the oxidation of hydrogen sulfide. That's certainly the case. But the electrons have to come from somewhere. There are electrons that are needed to reduce the carbon in the CO2 to the level that we see in organic material. So you need to know that, but you don't need to know the details about what's going on. But let me give you a little bit of the details. So we can figure out that oxidation state by knowing that each oxygen is at an oxidation state of -2 in this equation here. So that means the carbon must be at a +4 here. If we go over to this side of the equation, same thing, -2 for oxygen, +1 for each of the hydrogen atoms. That means the carbon in organic material must be at an oxidation state of 0. So we need some 4 electrons to go from the oxidation state of the carbon in CO2 to the oxidation of carbon in organic material. And the question is, where do those electrons come from? And what's the answer? Well, before we get to the answer, let's go make another parallel and talk about where those electrons come from for plants and algae, phytoplankton, that carry out what we call oxygenic photosynthesis, or they are oxygenic photoautotrophs. And that gives you an idea about where those electrons come from. They come from water. And so this is a diagram I presented in one of the first lectures, which I'm sure you've forgotten and suppressed or deleted from your memory banks to make room for all the new material. But I want to draw the parallels between what's happening with photosynthesis driven by light energy versus the chemoautotrophy that's driven by the oxidation of inorganic compounds. So all this is the same in the sulfide-oxidizing bacteria. What's different and really crucially is where those electrons are coming from. So the light energy, of course, is making the ATP, and it's because of the light energy and the unique pigments, in particular chlorophyll A, that these organisms have. They are able to use water as the electron source, and they are able to split water. Basically, they're able to oxidize water. Kind of weird to think about, but they're able to burn water and release those electrons, which go to reduce CO2 to the oxidation state that we see in organic material. So the same thing is happening with these hydrogen sulfide oxidizing bacteria. The huge difference, of course, is there's no sunlight, there's no pigments involved, but there are membranes involved. That's not too crucial for you to know now, but what is important for you to know is that hydrogen sulfide is a source of not only the energy, but also the electrons that are needed for carbon fixation by these organisms. And again, the same Calvin-Benson-Basham cycle, or Calvin cycle for short, is used by both sets of organisms. So everything else is the same. The only crucial difference is the source of electrons is H2S for these organisms and water, H2O, in the case of the oxygenic photoautotrophs like higher plants and phytoplankton. So there's the equation that we've seen many times already. Now it's carried the oxidation is carried all the way to sulfate, the most oxidized form of sulfur in the biosphere. Okay, so what should you know from all this? Well, you should have known already before this short lecture that hydrogen sulfide is the energy source that's used by these bacteria. And these bacteria in turn are the prime producers. They support their growth from the H2S. They use that H2S for energy. They make ATP from it. And that's necessary for carbon dioxide fixation. Of course, these bacteria are the prime producers and are the base of the food chain and support all the other vent organisms that we see there. And the other main point that was the main reason for doing this little short mini lecture is to point out that the oxidation of hydrogen sulfide also provides the electrons. And those electrons are also as crucial for reducing carbon dioxide to organic material. And so you need energy, that's for sure, but you also need the electrons, and that's what H2S is also doing in this system. So I hope you now appreciate some of the basics outlined of the physiology of these really important organisms that support all life, the hydrothermal vents.